All right, so let's see. So yesterday we started 6.5, and we actually got most of the way through there. We're going to look at the last part today, which is um, may seem just a little bit weird, but we talked about how we can write a complex number, so an a plus bi, that's standard form. How we can write that in trig form, graph it on a complex plane. We talked about how we can do some arithmetic with it. Um, and if we've got it in trigonometric form, we find a modulus, or that's the radius that sits out front, and we find a direction angle. So it's kind of like working with a vector, but not really. All we're interested in is that point that would be right at the end there. But a lot of the same tools that we learned with vectors can come in handy here. So we talked about how we can find the product and the quotient of two complex numbers in trig form. So if we're multiplying complex numbers in trig form, we multiply the radii, or the moduli, and add the angles. If we're dividing, we divide the moduli, and then we subtract the angles. We usually want to write the answer in trig form, and we want to write it with the smallest positive angle that's coterminal with this one that we get when we add them together. So when we added 150 and 300, we got 450. That's the idea of the right answer, but we'd usually write that as the smallest positive angle that's coterminal. And then, of course, we changed it into standard form just to double check and make sure. And then there's that shorthand, that cis notation, if you want to think of it that way. If you want to use that, that's fine. Pardon me. I'd prefer you not use it all the time. I mean, make sure you do this some of the time. Okay? We did this problem right here where we multiplied the two of these together, and then we double checked that we got the same answer either way, whether we did it in standard form here or did it in trig form here. And then we talked about how we can raise a complex number in trig form to a power, and we came up with this formula right here. And this is where we left off. We left off with something called the Mauves Theorem. And the Mauves Theorem basically says if you're going to take a complex number in trig form and raise it to a power, you raise the radius to that power and you multiply the angle by that number. Okay? So we did a very easy one here. And then I said I'd like it if you could do this one right here. So let's go ahead and write down the answer here. If this is what z is, and I raise that to the fifth power, I take 4 and I raise it to the fifth. So what is 4 to the fifth power? 1024. So 1024 is going to be the radius, or the modulus. Okay? And then if I multiply these together, I am going to write cis on this one. If I multiply that by 5, I end up with 1500 degrees. Now, again, if it's written in degrees, great. You can go ahead and leave the answer in degrees. If it's written in radians, make sure you write the answer in radians. So are we going to leave it as 1500 degrees? Nope. We're going to take this and we're going to subtract 360 and subtract 360. We're going to subtract 360 until we get something that's between 0 and 360. And let's see, I think we have to subtract 360 4 times. Is that right? I think 4 times. So it's 1024. And I'm going to write cis. Let's see, is it 60 degrees? And that would be the answer. Okay? Any questions? Please make sure you pay attention to the instructions. If they say write the answer in standard form, would we be done right here? We wouldn't. We'd have to do 1024, and we'd have to multiply it by the cosine of 60 degrees plus 1024 I sine 60 degrees, and then put it in standard form that way. Okay? All right. Everybody good? Okay. Pretty easy so far. A little bit on the weird side. Kind of amazing that it works that way, but we can figure it out, right? Okay. So here's what I want you to think about. Okay. This is what happens when we raise a complex number to a power. So remember, the radius on this one was 2, and by the time we raised it to the 8, the radius was 256. And the angle used to be 30, and then it ended up being 240. On this one, it was 300, ended up being 1500, and the radius was 4, it ended up being 1024. So here's what happens. Say I've got this complex number, and it looks about like this. The complex number is right there. When I raise it to a power, a couple of things happen. Okay, I kind of extend the radius. It gets much longer. The modulus gets much longer. And I take the angle and I kind of wind that up. Okay? So maybe it ends up right here. Okay? So it's this long, but we wind up the angle and make it end up in the right place. So raising a complex number to a power does two things. It scales up the radius, or the modulus if you want to think of it that way, and it winds up the angle. Okay, since we're multiplying the angle by whatever the power is, it's going to make that angle much bigger than it used to be. Okay? So just like most things in math, we learn how to multiply, then we learn how to divide, we learn how to raise to a power. Now we're going to learn how to find the nth root of a complex number. So we're going to be finding roots of complex numbers in trig form. Okay? So I've got a question for you. Why is 2 the cube root of 8? Because 2 to the third is equal to 8. Okay, and why is negative 4 one of the square roots of 16? Because if I take negative 4 and do what with it? Square it, I end up with 16. Okay, so this is why this is the cube root of 8, and this is why negative 4 is the square root of 16, or at least one of the square roots of 16. Okay. So we need to understand that definition so that the idea of the root of a complex number can make sense. So if I've got u equals a plus bi, so if this is a complex number, okay, if that's the nth root of z, so if this right here is the nth root of z, so it's kind of like saying 2 is the nth root of 8, okay, then u to the n would have to be a plus bi raised to the n. That's how we'd know for sure that it's actually a root. If it was the second root, you can raise it to the second power and it equals the number that we want. Just like here, 2 is the cube root of 8 because if I take 2 and I cube it, I end up with the number that I want. So if the number that I want is z, I've got to be able to take that root that we think it is, raise it to the nth power, and end up with z. So how do we find the nth root, second root, fourth root, 18th root, 7th root of a complex number? So if we use de Mauves theorem and kind of gloss over a couple of the details, we can actually figure out what this would be. So if I have z to the n equals r to the n, and then cosine n alpha plus I times sine n alpha. So this is de Mauves theorem, right? If we raise it to a power, we raise the radius to that power, and we multiply the angle by that power, right? So let's say we've got that and we want to get back to the original number z. So we don't want to raise z to the nth, we just want plain old z, okay? Then we're going to take the nth root of both sides of that equation. That makes sense, doesn't it? If I took 2 and I cubed it and I got 8, if I wanted to get back to 2, I'd take the cube root of this side, cube root of this side, and I'd take the cube root of this side. So I'd get right back to the 2 that I wanted, or that I started with, okay? So I'm going to take the nth root of both sides. So that's going to be z to the nth, r to the nth, cosine n alpha plus I sine n alpha. Okay, I'm not going to rewrite this side at all yet. But you'll notice that I've got this times this expression right here. So that properties of radical says if you've got a multiplication problem underneath the radical, you can break it into two parts of the radical and then just multiply the end results. So what I'm going to do is I'm going to do r to the nth right here. And then I'm going to do the cosine of n times alpha plus I times the sine of n times alpha right here. So what should this give me if I carried this out? That just give me z, right? What should this give me? Just give me r. Okay, see how I'm back to the right length for the radius? Okay, so it's pretty clear to do what to do with each one of these. But what do I do right here? Well, let's stop and think for just a second. When we used de Mauves theorem, we multiplied the angle by n when we were raising it to the nth power. So if I was raising it to the nth, I'd multiply it by n. So it should kind of stand to reason that if we're going to take the nth root, what would I do with n and these guys right here? I'm going to divide. Okay, we're going to divide by n when we're finding the nth root. So this is going to be the cosine of n alpha over n plus I sine n alpha over n. And what's going to happen? These are going to cancel off and I'm all set. So I'd get z equals r cosine alpha plus I sine alpha. And I'm right back to where I begin. Now, let me just point out another reason why it should make sense that we divide. If I did the third root of x, and I wrote that with a radical, or excuse me, with a rational exponent, that would be x to the 1/2, right? Or sorry, 1/3, 1/3. So if I'm raising this, if I'm taking the nth root, what I'm really doing is I'm raising this to the 1/n power. So it's kind of still like multiplying by 1 over n. Same thing as dividing by n, okay? So this would be divided by n, and that would be divided by n. Okay, now notice that I've changed, so I've got thetas here, okay? So if z equals r cosine alpha plus I sine alpha, then the nth root of that would be, take the nth root of r, take alpha divided by n, and take theta and divide it by n, and take theta and divide it by n on both of those. Remember, those angles are always going to be the same thing, okay? Okay, it's not quite that easy, okay? It's close, but it's not quite that easy. This is the actual formula, and we're going to fill this in, okay? So if z equals r cosine theta plus I sine theta, then if I want to take the nth root, here's what I do. I take the nth root of the radius, I take theta and I divide it by n, but I've also got this other thing here. I've got 2k pi. And this is going to be 2k pi over n. Where k can be any integer from 0, 1, 2, 3, 4, all the way up to n minus 1. So we had this part figured out before, and we had this part figured out before. So where did the 2k pi come from, and where did the n minus 1 come from? Why do we have so many numbers that we're going to need to plug into this formula to get all the roots? Okay? So the answer comes from thinking about what happens when we raise a number, a complex number, to a power. Okay? We scale up the radius, generally make the radius longer, okay, and we wind up the angle. That's what happens when we're raising it to the nth power. When we're finding the nth root, we're going to do the exact opposite. Okay, so the first thing we're going to do is we're going to scale down the radius. We're going to take the nth root of the radius. Okay, and we're going to unwind the angle. So if it makes sense that we scaled up the radius and then wound up the angle when we're raising it to the nth, when we raise it to the 1/n, or when we take the nth root, we're going to scale down the radius and then we're going to unwind the angle. Okay? Now, here's where the problem comes in. And this is just kind of a picture of what happens, and hopefully this makes sense. Okay? So let's say that it's our number looks like this right here. So when we scale down the radius, it's this long. Let's say it has to be this long, and it's got to be pointed in this direction right here. So let's say, oops, let me do this in blue. Let's say this is the right answer right here. Let's say that's the correct answer. Okay. Well, when I scale it down and then when I unwind it to get back here, I might go past the correct angle several times as I unwind. And if I unwind it n times, I'm going to go by the correct angle n minus 1 times. So it's kind of like we can figure out the right angle to begin with, but then as we unwind it, we're going to go past that same place one less times than the number of times we unwind it. Okay? Now, that's not a technical definition, that's not a proof or anything like that, but that is in fact what's happening. Okay? We're going by an angle that would produce the right angle, n minus 1 times. And if you include 0, we end up with n roots. Okay? So that all sounds really complicated, but in practice, it's actually darn easy to do. So here's what we're going to do. Given that complex number, find the, find the indicated roots. So we want to find the cube roots of 8 cosine 30 plus I sine 30. So if we're going to find the cube root, what's n? Cube root? 3. Okay. N is going to be 3. So remember how this formula works. Okay. We take the nth root of the radius. We take theta plus 2k pi over n, or this could be 360k, which is what we're going to do here. Okay. So we're going to take the cube root of 8. Then we're going to do cosine. Theta is 30 degrees plus 360k over 3 plus I sine 30 degrees plus 360k all over 3. Now, I'm going to do this one the long way, and then I'm going to show you a shortcut in just a second. Okay, does everybody agree that's what the formula represents? And I'm going to use k equals 0, k equals 1, k equals 2. Do I need a 3? Nope, because if I do 3 minus 1, that's 2, so I'd stop when I get to n minus 1. I stop when I get to 2. So how many cube roots am I going to get? 1, 2, 3. I'm going to get 3 cube roots. If I do 4, I'm going to get 4 fourth roots. If I do 8, I'm going to get 8 eighth roots, and so forth. Okay? So here's what I get for the radius. I get 2, and then I get cosine of, if I plug in a 0, I get 30 divided by 3, so that's going to be 10 degrees. And that one works out the same way there. So that's for k equals 0. Let's let k equal 1. Cosine. If k is equal to 1, I end up with 390 divided by 3, so what's that? 130 plus I sine 130. And if I let k equal 2, the radius is always the same, it's just the angle that changes. Cosine of, that would be 720. 2 times 360 is 720, plus 30 is 750. 750 divided by 3 is 250. Plus I sine 250. Okay. Now, just for the heck of it, let's see what would happen if I said, well, why did we have to stop at 2? Let's say we said k equals 3. This would be 2. This would be the cosine of, okay, let that equal 3, so that's going to be 1080, right? Plus 30. That's going to be 1110. What's 1110 divided by 3? 370. Okay. Does anybody see why we don't need this? Brandon? Okay, it's over 2 pi. It's over 360 degrees. That's one reason. I'll take that. There's another better reason. Lynn? When you subtract 360 from this, you get 10 degrees. So this one is coterminal with that one. So this one is right on top of the first one we found. So this right here, those are all the answers. Anything else we did, if we kept going around, we just get answers that are coterminal with this. Okay? Yeah.
So would you always stop at 2?
No, if it's 3, you always stop at 2. If it's 4, you stop at 3. If it's 8, you stop at 7. Okay? Because we do 0 up through n minus 1. So on this one, it's 3, so I get 1, 2, 3 answers. If n was equal to 4, I'd do 0, 1, 2, and 3. 1, 2, 3, 4 answers. Yeah.
On this one, it goes up by 120 every time. So will that like happen with everyone? Not necessarily 120, but it will be a pattern every time.
It is a pattern every time. So let's take a look at this. One thing you can do to make this problem a little bit easier is, and I'm going to write this up here, this is going to be 2, and then this is going to be cosine of, what if I break this up into 30 divided by 3, that's 10 degrees, and what would this be? 120k plus I sine 10 degrees plus 120, okay? So if I plug in a 0, the first answer is 10. If I plug in a 1, the next answer is add 120, so you get 130. If I plug in a 2, I add 240, so that's going to be 250. Or I can get the first answer. This is the easiest way to do it. Get the first answer. Take 360, divide it by whatever n is. You're going to get 120. Get the first answer by dividing the angle that we have here by 10. Or sorry, by 3. You get 10. And then add 120, get 130, add 120 again, you get 250, add 120 again, you'd get 370, but again, that's coterminal. If you're finding cube roots, you only want those right there, okay? That's a nice little shortcut, very good. Any questions? Okay, let's do that on this one right here, and this problem is a little bit different, but you do have problems like this on your assignment, so take a good look. This says the 4th roots of 81. We want all 4 roots of 81. So, what's n? How many answers are we going to have? We're going to have 4. We're going to get 4 answers. Now, here's what people struggle with. They look at this and they go, wait, 81, I can just take the 4th root of 81, I can plug that into my calculator, it gives me an answer. But it doesn't give you all the answer, it doesn't give you all the complex answers. Okay? So, the first thing we want to do is we want to write this in trig form. So think about where this is. 81 is a real number or an imaginary number? Real. It's way over here. It's over here at 81. So, what is the radius for that particular number? What's the modulus? 81. What's the angle? The angle is 0. Good there? Okay, find the 4th root of 81 so we can figure out what the radius is. What's the 4th root of 81? 3. So I'm going to have a 3 here. Okay, let's do the shortcut here. The angle is going to be that one divided by 4. So what's 0 divided by 4? First answer is 0 degrees. How do I figure out how much to add to get to the next one? 360 divided by 4 is 90. So the next one is 3 cosine of, add 90. What's the next one? And what's the last one? And why do I stop there? Why do I not add another 90? That would be 360, and that would be coterminal with this one right here. And I'm finding 4th roots, so those are the 4 answers. Okay, any questions? Good? Okay, I want to show you something interesting. Okay? So remember I said that one reason why we might want to have a complex plane and graph complex numbers on the complex plane, write complex numbers in trig form, is because you can look at them and you can see some interesting patterns. So let's take this one right here and let's plot these numbers. This one has a modulus of 2 and a direction angle of 10. So kind of think of it as a vector. So 10 degrees is about right here. And I'm going to go out 2 units, so I'm going to put it about right there. Okay, so there's my first one. 2 degrees at an angle of 130. Well, 130 is about right here, so I'm going to go out 2 units, and I'm going to put it right there. So here's the first one, here's the second one, and then the third one is 2 units out at an angle of 250 degrees. Well, this is 270, 250 would be about right here. Okay, do you notice anything about those? And if you do, great. If not, you should definitely notice something about these. Let's graph these. Radius is 3, direction angle is 0. So we're going to go out 1, 2, 3. Radius is 3, direction angle is 90. Radius is 3, direction angle is 180. Radius is 3, direction angle is 270. What do you notice about these? Yeah. Perfect. Okay, that's the right way to say it. They are all equally spaced. Once you find the first one, the way you find the next one is 90 degrees here, 90 degrees here, 90 degrees here, and 90 degrees here. Once you find the first one here, how many degrees was it from here to here? 120. 120 and 120. So that's a visual way of saying once you find the first angle, and finding the first angle is a piece of cake, take the angle, divide it by n. We're finding cube roots, so divide by 3. The first angle would be 10. And then we're going to divide the circle up into 3 equal pieces, so they're all equally spaced. Okay? The fancy word for these are roots of unity. So if we were finding 6th roots, we would find them that they were all 6 of them equally spaced. Okay? Wherever the first one started, the next one would be how many degrees away from it? If it were 6th roots. 60 degrees. 360 divided by 6 would be 60. Okay? What if we were finding 9th roots? How many degrees would there be between each one? 40 degrees. Does that make sense? Okay? So hopefully that's pretty easy. And then you've got some problems. These are the last ones that we're going to take a look at, and then you can do your assignment. It says, find all the complex roots of that equation and all the square roots of this number right here. So sometimes people will look at this and they'll go, wait a minute. Okay, this doesn't have anything to do with what we're doing here. This is an equation. It's not a complex number in trig form or anything like that. Well, let's move this over. How would I solve that? I'd take the 4th root of both sides, right? So what I'm doing is I'm finding the 4th roots of negative 16. If you're going to find them using this method, here's what we do. Negative 16 is a real number. It's right there. How far away is it from the origin? 16, not negative 16, 16. What is the direction angle? 180. So in trig form, our original number is 16 cosine, and I'm going to do this in radians, okay? Cosine pi plus I sine pi. Everybody good? So here are my roots. Take the 4th root of that. What do I get? 2. Divide that by 4. What do I get? Pi fourths. Okay, so I'm going to write cis pi fourths. There's one of them. The next one would be 2 cis. Now stop and think about this. How far is it around the circle? If I'm in radians. 2 pi. How many pieces are we dividing this into, since we're finding 4th roots? That's how equally spaced they need to be. They all need to have pi halves in between them. It's more difficult with radians, but we can do this. So this one's not too bad. So once I've got the first answer, what do I do to get the next one? Add pi halves. What do you get? 3 pi fourths. 2 cis. What's the next one? 5 pi fourths. And the last one? Good? Okay, watch. Watch. this would be here, this would be here, this would be here, and this would be here. All equally spaced, right? Okay. Any questions? Okay. Would you do that one, please? First thing you got to do is write it in trig form. Real or imaginary here? Imaginary. Go up or down? Down. How far is it away from the origin? What's its radius? What's its modulus? Positive 25, not negative. Cosine, you want to do degrees or radians? Okay. What's the angle in radians? 3 pi halves. Okay, there's the original one. Now I want to find the square roots. How many answers am I going to get, first of all? Going to get 2. What's the modulus for both of them? What's the radius for both of them? 5. First answer I get by taking this and dividing by 2. So that's going to be 3 pi fourths plus I sine 3 pi fourths. And how do I go from one answer to the next answer? Take the circle, and we want to equally space them out, and we're going to have 2 answers, so we're going to space them by pi. So I'm going to add pi to this one right here, and I get 7 pi fourths. So I end up with an answer, let's see, right here, and an answer right here. So they happen to be straight across from each other, but you can see that there's 180 degrees or pi in between each one of them. Any questions? Okay. Let's see. Maybe we could try and solve this one algebraically. So you can just watch. You don't have to write this down. I wouldn't expect you to do this. But if I solved this algebraically, here's what I'd get. I'd move this to, whoops, that's the 4th power. I'd move this to the other side, and that would be a negative 16, right? And then I'd have to take the 4th root of negative 16. Do we know how to do that? What's that? It does have something to do with 2i. Okay? But in order to do that, you'd have to do like a square root of a square root. Okay? So maybe we could rethink this, and maybe we could rewrite this as maybe a difference of squares. So could I write this as x to the 4th minus something raised to the 4th? What if it were 4, let's do this, 2i, would that work? Or let's see, that'd have to be plus. Would that work? Let's see, what if we wrote it as 2i squared and raised that to the second and wrote that as x squared squared? Okay. Solving these algebraically can be kind of tricky. Okay. So relying on, I mean, this was relatively easy, wasn't it? Okay. All right. Any questions?